Why does a simple light bulb implode instantly beneath the waves? Which underwater mystery haunts you most? Tell us your thoughts below. Air pockets inside bulbs collapse under massive water pressure instantly. Water conducts heat away faster than air, causing circuit shock. Engineers use specialized synthetic oils to balance internal housing pressure. Saltwater eats through standard steel, like a hungry shark feeding. Water bends light, making your camera focus miss the target. Red light disappears within meters, leaving only ghostly blue hues. We build cameras inside titanium shells to survive the depths. That detail becomes important later. Water pressure increases by 1 atmosphere every 10 meters down. Standard glass lenses shatter instantly under intense deep-sea pressure. Engineers use thick acrylic domes to distribute force more evenly. Tiny gaps allow water to crush sensitive internal electronic circuits. Powerful lights get hot while the ocean remains near freezing. Rapid temperature changes cause metal housings to warp and leak. We fill light housings with oil to equalize internal pressure. Unlike air, oil refuses to compress when the depths push. This simple liquid prevents the housing from imploding during descent. Electronics stay safe because the pressure remains perfectly balanced inside. Water pressure increases by 1 atmosphere every 10 meters down. Standard camera housings would implode like a soda can instantly. Tiny gaps between seals allow water to enter at speed. Flat glass ports fail, while domes distribute force much better. Electronics generate heat, but water conducts it away too fast. Particles in the water column scatter, light back into lenses. Red wavelengths vanish first as light travels through deep water. Engineers use titanium alloys to resist corrosion and extreme pressure. Some housings are oil-filled to match the outside pressure. Every design choice is a compromise between clarity and survival. Standard glass bulbs shatter instantly under immense deep-sea pressure. Engineers use thick acrylic domes to resist that heavy force. Rubber O-rings compress tighter as the water depth increases further. Internal heat has nowhere to go in a vacuum sealed. Surprisingly, we fill camera housings with oil to equalize pressure. This fluid prevents short circuits while supporting the outer shell. Light behaves differently when traveling through dense pressurized salt water. But how does the oil stay inside without leaking out? Flexible bladders allow the internal volume to shrink and expand. It is a delicate balance of physics and clever engineering. Water pressure increases rapidly with every meter of depth reached. Standard camera glass would shatter under these intense oceanic forces. Tiny microscopic gaps allow water to penetrate even solid steel. Water scatters light differently than air, blurring your captured images. Electronics trap heat, yet water cools the housing too fast. Saltwater eats through metal faster than you can possibly imagine. Red light vanishes instantly, leaving only blue and green hues. But the real danger is actually the internal air pocket. Air pockets collapse inward, turning cameras into expensive metal confetti. Engineers must fill housings with oil to prevent total collapse. Water pressure at depth crushes air pockets inside standard devices. Engineers must fill every internal gap with specialized pressure oil. Without air, electronics overheat because heat cannot easily escape outward. Titanium hulls act as massive heat sinks for internal components. A single microscopic hair ruins the seal of deep cameras. Standard white light bulbs vanish quickly in the deep ocean. Red wavelengths are absorbed within just 5 meters of depth. We use specific blue LEDs to penetrate the dark abyss. Curved glass ports prevent the refraction errors of flat glass. Durable gear is heavy, making it harder to deploy quickly. Standard camera bodies implode under the ocean's immense crushing pressure. Rubber O-rings must hold perfect seals against thousands of pounds. Without airflow, internal circuits overheat inside sealed metal housings. Flat ports cause magnification errors that distort every single shot. Water absorbs red light waves within only a few meters. Artificial light is mandatory to restore natural colors underwater here. Saltwater eats through unprotected metal parts like hungry tiny termites. But engineers use oil-filled housings to equalize internal pressure levels. Oil does not compress, keeping the casing from snapping inward. This simple fluid trick allows cameras to reach absolute depths. Standard camera glass would shatter instantly under deep ocean pressure. Engineers use spherical housings to distribute force evenly across surfaces. Synthetic sapphire windows are used to prevent micro cracks under load. Any trapped air inside electronics will implode during rapid descent. If you enjoy this engineering insight, please hit that like button. Filling housings with silicone oil makes internal components effectively pressure neutral. Hit the subscribe button and press the bell icon to get updates. Heat dissipation is ironically difficult when surrounded by freezing water. Double O-rings create a redundant barrier against high-pressure leaks. This complexity explains why deep ocean footage remains so expensive. Water pressure increases by 1 atmosphere every 10 meters downward. Standard rubber gaskets fail under the weight of deep oceans. Ordinary glass windows shatter instantly when subjected to extreme pressure. Sealed housings trap heat, causing delicate internal electronics to melt. Engineers fill cameras with oil to equalize internal pressure differences. Oil is incompressible, protecting circuits from the crushing outside force. Water refracts light differently, distorting images captured by standard lenses. Specialized dome ports are required to maintain clear, undistorted focus. Titanium housings resist corrosion while maintaining necessary structural, rigid strength. Building these machines costs more than buying a luxury car. Water pressure at depth forces air pockets into tiny fractures. Standard rubber seals fail when they deform under immense force. Land cameras use air to cool components during heavy operation. Underwater electronics boil in their own heat without airflow cooling. Curved glass ports bend light differently than flat air lenses. Red light disappears within meters, leaving only blue and green. Thin glass bulbs implode instantly once they hit deep water. Engineers fill entire housings with oil to equalize internal pressure. Oil does not compress, so the casing maintains structural integrity. Your camera is just a tiny, very expensive pressurized submarine. Standard glass domes shatter under the ocean's immense crushing weight. Engineers now use synthetic sapphire to resist these extreme pressures. Water steels heat away from electronics faster than stagnant air. Metal housings act as radiators to keep internal circuits cool. Water filters out red light within just a few meters. Underwater bulbs must emit specific wavelengths to restore natural colors. Saltwater destroys exposed circuitry faster than any other common element. Double O-ring seals prevent even a single drop of leakage. Some cameras use oil to balance pressure inside the housing. Liquids do not compress, protecting delicate sensors from imploding inward. Water pressure at depth crushes standard air-filled glass housings. Engineers use thick synthetic sapphire to prevent catastrophic implosion failures. Without air convection, light bulbs overheat and melt their internal circuits. Heavy aluminum housings pull heat directly into the cold water. Water bends light differently than air, distorting every captured image. Dome ports are essential to maintain sharp focus underwater today. Tiny particles of sand can destroy rubber seals instantly forever. Saltwater eats through most metals unless they are perfectly anodized. Building for the abyss requires sacrificing weight for sheer durability. The facts remain, and the search for truth continues.